Hello. In this lecture on demand, we will be talking about functional groups. This is a very important idea for organic chemistry because there are literally millions of known organic compounds, and organic chemists have to organize them somehow. And so we organize them into what are called families, and each family has a separate functional group. So that's what we're going to be talking about. At the same time, we're going to be talking about ways organic compounds can be drawn. There are several different formats that organic chemists use for drawing the structures of compounds. Compounds whose molecules have the same kinds of groups of atoms often have similar chemical and physical properties. For example, alcohols are compounds that have an OH group attached to a saturated carbon. And we'll think about what that means here, but basically a saturated carbon with an OH group is called an alcohol. Alcohol is the family name or class name, but the OH group is called a hydroxyl group. So it illustrates the difference between the group of atoms, which is called a hydroxyl group in this case, and the family, which is called alcohols. Now, on this slide, I've shown some structures of compounds that are in fact alcohols. Notice that this compound has a carbon with 3 hydrogens and an oxygen. This is what's called a saturated carbon because it doesn't have any double bonds to it. It also has an OH group, that is an oxygen with a hydrogen attached. Therefore, it is what we call an alcohol. Now, I want to show you how we draw some of these structures. This structure can also be drawn as CH3OH. Notice it's a carbon with 3 hydrogens and an OH, therefore it's drawn CH3OH. This is what's called a condensed structure. In a condensed structure, each carbon is listed individually in order, and then what's attached to it is listed, in this case 3 hydrogens and an OH group. Notice that this structure has 2 carbons, 5 hydrogens altogether, then an OH group. In other words, a carbon with 3 hydrogens called a CH3, then a carbon with 2 hydrogens, CH2, and then the OH. So CH3, CH2, OH. Again, this is the condensed structure. This compound is another example of an alcohol, not the same alcohol as this one over here. Now, notice this kind of structure right here. This is what's called a bond line formula, and it's very arcane, but easy to draw. You have to know how to interpret it. Each time you come to an angle, that represents a carbon atom and as many hydrogens as it can hold. Now, since a carbon at this position already has 2 bonds to it, it can hold 2 more hydrogens, because remember, carbon has to have 4 bonds. So this, just a bend in or an angle between 2 lines, represents a CH2 group. Here's the thing, when you come to the end of a line like this, it also represents a carbon with as many hydrogens as it can hold. So that point right at the end of the structure represents a carbon. It's that carbon with 3 hydrogens, and we know there have to be 3 hydrogens there because carbon has to have 4 bonds, and therefore, since it already has 1 bond, it has to have 3 more bonds, and we assume that they are to hydrogens. Here's another tricky thing. Notice that we come to an end of a line over here as well. Does that mean there's another carbon there? Nope. If you come to the end of a line and there's a different atom, in this case an oxygen, it means there's not a carbon. So at this end of a line, when there's nothing else showing, that means there's a carbon. At this end of a line, when you get to the end of the line, it has an oxygen, so that means it's not a carbon. So this is to be interpreted as CH3, CH2, OH. Not 3 carbons, but only 2. So that's CH3, CH2, OH. Here's another example of an alcohol, and it's an alcohol because it has an OH group attached to a saturated carbon, saturated meaning having 4 single bonds. So this is an alcohol. Notice that it's CH3, CH3, CH2, 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 OH. So this condensed structure is the same as this more blown up structure. And then this is the bond line formula. So that carbon is a CH3, that's a CH2, that's a CH2. There is no carbon here, but an OH instead. So 3 carbons and an OH, representing 3 carbons and an OH. Notice this structure is also an alcohol because that carbon where the OH is attached is a saturated carbon. In other words, it doesn't have a double bond to it. There is another double bond in this structure, but it's not on this carbon, rather it's on the carbon next to it. So this is an alcohol because it has an OH on a carbon that's saturated. Doesn't matter whether these carbons are saturated or not. Now notice that, again, this is 3 carbons with a double bond between the first 2, so that's a CH2, notice carbon with 2 hydrogens, a CH, carbon with 1 hydrogen. Now the double bond is shown specifically in the condensed structure because that's the only way to indicate that there is a double bond in that structure. and then CH2, CH2, and then the OH. So again, 3 carbons with a double bond and an OH. Then we get to the bond line formula, and we see we get to the end of a line right here. So that's a carbon with how many hydrogens? Only 2 in this case, because it already has 2 bonds to it. So in order to make a total of 4 bonds, we know that there must be 2 hydrogens at that carbon. And then this carbon has 1 hydrogen on it because it already has 3 bonds, and therefore can only have room for 1 more hydrogen. And then this carbon must have 2 hydrogens because it has 2 bonds, and to make a total of 4, therefore it must have 2 other hydrogens. And then we get to the OH. Remember, there's no extra carbon at this end of the line because there's an oxygen there instead. Okay, I've drawn some more structures on this slide, but remember, the idea here is that these are not alcohols. Notice that this oxygen has an OH group, so it seems like it should be an alcohol, but notice that the oxygen is attached to a carbon with a double bond to it, and therefore that's not considered to be an alcohol. This is a different family of compounds called phenols. Again, don't worry too much about it other than to recognize that it's not an alcohol because the carbon to which the OH group is attached is not a saturated carbon. It's a sp2 or double bonded carbon. Similarly, this compound right here has an OH group, so it seems like it should be an alcohol, but it's not because the oxygen of the OH group is attached to a carbon with a double bond. In this case, it's a C double bond O, which makes this whole thing with the OH group and the C double bond O a different functional group that we will consider here in a few minutes called a carboxylic acid. But if you have an OH attached to a C double bond O, it's not an alcohol, it's a carboxylic acid. Now you might want to take a minute and interpret this bond line formula and see how it corresponds to this more expanded formula. And similarly, this condensed structure, CH3, CH2, C double bond O, OH, which is the same as this. And then again, this bond line formula to see if it fits with that structure. Now, let's get to some other functional groups. And I will tell you that these functional groups are found on page 17 in your textbook. And by the way, we will be talking about some functional groups in this video that are not listed in the list starting on page 17 in your textbook. There are a few extra ones that I think you need to be aware of. First of all, let's talk about alkenes and alkynes. This is 2 separate categories of compounds. Alkenes are compounds that have a C double bond at C in them. And so this is an example of an alkene. Notice that you can also write it as CH3, CH, CH2, and you might want to make sure that it corresponds. This is a condensed structure, and this is the bond line formula for that particular structure, this particular condensed structure. So this is an alkene because it has a C-C double bond. This compound looks pretty complicated, but it's also an alkene because it has a C-C double bond right here, so that makes it an alkene. Happens to be in a ring. Rings are perfectly acceptable in organic compounds, and so this is just a regular alkene. It happens to have a ring in it. Now notice that this compound also has an OH group in it. So does that make it an alcohol? And the answer is yes, it does. So this particular compound is both an alkene and an alcohol. It belongs to 2 different families, just like people can belong to 2 different families. I, for example, am an Armstrong, and I'm also a Waterman. So compounds can belong to more than one family. So this one happens to be an alkene and an alcohol. Notice that it has the double bond for an alkene and the OH group, a little bit more obvious in the bond line formula, but this is exactly the same thing as this, just a different way of drawing it. Now let's consider alkynes. Alkynes is a different category of compounds than alkenes, although similar in that alkynes have carbon-carbon triple bonds. So notice that this has a carbon-carbon triple bond. This particular compound is an alkyne. This is the condensed structure for it, CH3, C triple bond C, CH3. Now you might ask, is this CH3 written as H3C the same thing as the CH3 group? And the answer is yes. In this particular case, the CH3 group is written backwards. Notice that this is the bond line formula for it. We get to that end and it's a carbon with 3 hydrogens because it only has 1 bond, therefore it needs 3 hydrogens for a total of 4. This is a carbon with no hydrogens on it because it already has 4 bonds to it. This is a carbon with no hydrogens because it already has 4 bonds to it, and this is a carbon with 3 hydrogens because it already has 1 bond to it, so it needs 3 hydrogens. You need to practice looking at bond line formulas and determining how many hydrogens there are. Now, let's get to another category of compounds, another family called alkanes. These are different from all the other families for one very important reason. The definition of an alkane is that it does not have any functional groups. So notice that this carbon has only single bonds and only carbons and hydrogens. Therefore, this is what we call an alkane. It can be written as CH3, CH2, CH3, or this would be the bond line formula for it. But the point here is that it has no double bonds, no triple bonds, no oxygens, no nitrogens, or no functional groups. So that makes it an alkane. This also is an alkane because it has only carbons and hydrogens and only single bonds. This would be the bond line formula for it. But what makes alkanes unique among all families is that alkanes can only belong to the alkane family. So if you come across a compound that has some other functional group in it, then it is not an alkane. Notice that this particular compound has a carbon-carbon double bond, so therefore it's an alkene. Now you might say, but it also has saturated carbons here with CH3 and CH2, and so therefore this makes it an alkane. No, that's not true. Alkanes are only alkanes. If it's an alkene, then it cannot also be an alkane. Okay. This is the bond line formula for this particular compound, and this is the condensed structure for this particular compound. Okay, let's get to some of the functional groups that are in the chapter. First of all, amines. Okay, now amines have saturated nitrogen. That means a nitrogen with no double bonds to it, just 3 single bonds and of course a lone pair. By the way, I should point out in this particular lecture, notice that all these compounds I've drawn here, even if they have oxygens, for example this one, or these oxygens, notice that I have not put the lone pairs in. You need to recognize that when you see an oxygen like this with 2 bonds, that it automatically has to have 2 lone pairs in order to be a neutral compound. So lots of time organic chemists will not put in lone pairs, and you need to just recognize that they are there and put them in yourself if you want to. Same thing is true for this nitrogen right here. It has to have 1 lone pair in order to fulfill its octet and in order to be neutral. And so therefore you need to recognize that there is in fact a lone pair on that nitrogen even though it's not drawn in. Okay? This would be the condensed formula for it, and this would be the bond line formula for the same compound. But here's the definition. Amines have saturated nitrogen, no single bonds or no double bonds or triple bonds to it, and they need to be attached to a carbon that does not have a C double bond O. So no C double bond O attached to the nitrogen, and we'll see why when we get to the class of compounds called amides here in a few minutes. But this is an amine. Notice that this is also an amine because it has a nitrogen with all single bonds, and neither of the carbons attached to it has a double bond O. So therefore this is also an amine, slightly different kind than this one because this has an NH2 group. This only has an NH group. So it doesn't matter whether there's 1 carbon attached to the nitrogen or 2 carbons attached to the nitrogen, or in this case 3 carbons attached to the nitrogen. As long as they're all single bonds and no C double bond O's directly attached to the nitrogen, then it's an amine. So this is an amine, this is an amine, this is an amine. There's another class of compounds, aldehydes. Aldehydes have a C double bond O with a hydrogen attached to the carbon, and then another hydrogen or carbon also bonded to the C double bond O carbon. So notice that this carbon has a C double bond O, also has a hydrogen attached, which makes it an aldehyde, and also has another carbon attached. So, but at least one of these 2 groups attached to the C double bond O is a hydrogen. Therefore, this is an aldehyde. This is how we would draw this same aldehyde in a condensed form. CH3 for this carbon with 3 hydrogens, CH for this carbon with 1 hydrogen, and then the double bond O. So this is a condensed formula. This is the bond line formula for the same compound. Notice that this also is an aldehyde. Notice that it has a carbon right there, carbon with a C double bond O and a hydrogen, and then another carbon group on this side. So C double bond O with a hydrogen and another carbon group on the other side. These are examples of aldehydes. It's that C double bond O H group that make it an aldehyde. Ketones are similar to aldehydes. Ketones also have a C double bond O, but with 2 carbons attached to that carbon, no hydrogens. So if this carbon had a hydrogen on it, it would be an aldehyde. In this case, it doesn't. It has 2 other carbons attached to it, so it is a ketone instead. By the way, ketone is spelled K-E-T-O-N-E, not K-E-Y-T-O-N-E. Common spelling mistake there. But in any case, this is a ketone because it has a C double bond O with carbons on both sides. This would be the condensed formula, and this would be the bond line formula for that ketone. This is also a ketone because it has a C double bond O with 2 carbons attached, 1 on either side. This would be the bond line formula for it. So be able to recognize ketones and aldehydes and know that they are different from each other, although similar. Here's another category of compounds. These are called carboxylic acids. They also have a C double bond O, but notice that attached to the C double bond O is an OH group. So this, as we mentioned earlier, is what's called a carboxylic acid. It has a C double bond O and an OH, both on the same carbon. The other side may have carbon groups or hydrogens or lots of other things, but it's the C double bond O, single bond OH that makes it a carboxylic acid. Here's another example of a carboxylic acid, C double bond O, OH. Now notice that carboxylic acids are not alcohols, as we mentioned before. It has the OH, but the OH is attached to a double bonded carbon, therefore it's not an alcohol. Neither is this an aldehyde or ketone. To be an aldehyde, it would have to have a hydrogen directly attached to this carbon. To be a ketone, it would have to have two carbons directly attached to that carbon. This has neither, so it's not a ketone or an aldehyde. It's a new category of compound called carboxylic acids. One side note, you might notice that a property of carboxylic acids is that they are acids. We'll get to that when we learn about carboxylic acids later on, but the word acid is actually part of the name of the family, carboxylic acids. Here's another group that's not mentioned in the chapter, but which I think is pretty important, and that is ethers. Ethers are compounds that have a single oxygen in between two carbon groups. Right, so notice a single oxygen in here with carbon groups on both sides. In some ways it looks like an alcohol because it has a single bond O, but instead of having hydrogen on the oxygen, it has another carbon. So these are called, it's only an ether if both carbons on both sides have not a C double bond O. So if there's a C double bond O on one side or the other of this, along with a single bonded oxygen, then it's not an ether. We'll see what it is here in a few minutes. But ethers have just a single oxygen and then saturated carbons on both sides. Here's the condensed formula for it. Here's the bond line formula for it. And I'll let you interpret those on your own. Here's another example, oxygen in between with two carbon groups. In this case, a little bit more complicated carbon groups, but it's still an ether. And notice here, here's your oxygen in between and two carbon groups on either side. And then same thing drawn in the bond line formula. I think you can see the advantage of each of these kinds of formulas. This one shows all the carbons and hydrogens. This one just shows the bare bones of the structure, but makes it easier to interpret. This one's kind of in between, shows all the carbons and hydrogens, but in a little bit more condensed form than that. Now, here's another category called esters. The word ester is kind of similar to the word ether. You need to make sure you don't get them mixed up. Ethers don't have C double bond O's. Esters do have C double bond O's. So notice here's a single bonded oxygen with a double bond O next to it. So this is an ester because it has a C double bond O, then a single bond O, but not a hydrogen. If it had a C double bond O with a single bond OH, that would be a carboxylic acid. Instead, it has a C double bond O, single bond O with another carbon group, and that makes it an ester. So this is an example of an ester. This is a little bit more complicated ester because notice it has C double bond O, single bond O, then another carbon group. Notice also that esters are not ethers, even though they have that single bond O in between. Next door is a C double bond O, so that means it's not an ether. And it's also not a ketone or an aldehyde. It has a C double bond O, but it has an oxygen here instead of another hydrogen or a carbon, which would make it an aldehyde or ketone. Here's another category, amides. Amides are compounds that have C double bond O, just like carboxylic acids and esters and ketones and aldehydes, but it has a nitrogen attached to the C double bond O instead, and that makes it a compound called an amide. Now it's very similar to amine, which only differs by the letter N in there instead of a D, but makes all the difference in the world in terms of its properties because it has a double bond O next to the nitrogen instead of having just a saturated carbon there. If it's a saturated carbon, if all the carbons attached to the nitrogen are saturated, then it's an amine. If one of them has a C double bond O, then it's an amide, and they have completely different properties, so that's why they're different categories of compounds. Notice that we also have the condensed structure here and a bond line formula for this particular amide. Full structure of a different amide shown here, see double bond O, single bond N, same as this condensed structure. Now, one thing to notice, amides are not amines, as I said, because they have a double bond O next door to the nitrogen, and they're not ketones or aldehydes because the double bond O has a nitrogen attached to it instead of hydrogens and carbons. Now, here are some naturally occurring compounds. These are all things that are found in nature, and they all belong to one or more of the families that we've learned about before. Can you identify what family or families they belong to? Well, let's do a couple of these together. Notice that this compound has a carbon-carbon double bond in it, so therefore it's an alkene. It has another carbon-carbon double bond in it, so does that make it another alkene? Well, no, this is just an alkene. It happens to have more than one double bond in it. To be more specific, it's a diene, meaning two alkenes, but in terms of the family, it's just an alkene because it has a carbon-carbon double bond. What about this compound? Well, notice it has a double bond O, so does that make it an aldehyde, a ketone, an ester, an amide, or a carboxylic acid? And the answer is yes, but which one? Well, because it has an OH attached to the double bond O, that makes it a carboxylic acid. Okay, so this belongs to the family of carboxylic acids, but not ketones, aldehydes, alcohols, or anything else. What about this NH2 group attached to a saturated carbon? Well, that makes it an amine. So this compound is, besides a carboxylic acid, it's also an amine. And then what about this grouping down here? Does that NH2 make it an amine? Nope. Why? Because it has a C double bond O next to it. If it has a C double bond O next to it, then that makes it an amide. So this is an amide, this is an amine, this is a carboxylic acid. And so this particular compound belongs to three families: amides, carboxylic acids, and amines. Now what about these saturated carbons in here, that CH2, CH2, CH2? Does that make it an alkane also, because it has carbons and hydrogens with single bonds? And the answer is no, it's not an alkane. Remember, alkanes are different in that they can only be alkanes. If it's carboxylic acid or anything else, then it's not an alkane. So this is just amide, carboxylic acid, and amine, but not alkane. Found in, oh, by the way, this compound is an amino acid, one of the 20 essentially occurring amino acids, and as you might have surmised, it's an amino acid because it's got an amine and a carboxylic acid both in the same compound. This one is a metabolite found in the metabolism of sugars. What does this family belong to? Well, it's an alcohol because it's got an OH on a saturated carbon. Okay, there's a CH2 in here, and it's important to recognize it because there's that angle in there. That means there's a carbon with two hydrogens, and the OH is attached to a saturated carbon. Therefore, it is an alcohol, not a carboxylic acid. You might be tempted to say, well, it's got the double bond O with an OH attached to it. But the OH is not directly attached to that carbon. There's one in between. If it's not directly attached, then it's not a carboxylic acid. So this makes it an alcohol. This down here makes it also an alcohol, different alcohol in the same compound. And this makes it a ketone because it's a C double bond O with two carbons attached. So therefore this is a ketone and it's an alcohol. It happens to be a diol, meaning two OHs in the same compound. What about this one? And what is all of this with a CH2, 2, and then in parentheses 14? Well, that simply means that we have a CH3 group, and then we have a series of 14 CH2s. It just makes it easier to write it this way, but it's actually CH3, CH2, 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 and so on. And then a C double bond O, then a single bond O, then another carbon with a bunch of CH2s, and then a CH3. This comes from beeswax. What kind of compound is this? What family or families does it belong to? Well, notice it has a C double bond O with a single bond O and then another carbon group. That makes it an ester, not an ether, not a carboxylic acid, not a ketone or aldehyde, but an ester instead. Thank you.